Okay, this problem is the exact equivalent of the problem we did before with the spherical conductors, but now for the case of cylindrical conductors. So here we have a cylinder. It's a conductor in the shape of a cylinder of radius a, and it has a certain length, a long length, a very long conductor. We're going to assume it's infinite for all our calculations. And then there's a region of empty space here between A and B. And then from B to C, there's a cylindrical conducting shell that has an inner radius B and an outer radius C. And then after that, it's empty space again. And given in the problem that you have charge per unit length 2 lambda on the inner conductor and charge per unit length minus lambda on the outer. So the charge per unit length on the inner conductor, it's equal to a value 2 lambda, and here it's equal to a value of minus lambda. And they didn't tell us for the outer conducting shell if the charge is on the inner surface, how much it is, and on the outer surface, how much it is. They just said the total charge per unit length is minus lambda. So the first thing we want to discuss is what do we mean by giving charge per unit length in this situation. It's a bit different than what we took before. Before we said lambda was charge per unit length on a contour that had no thickness, no size, only a certain length. So the thing is, we're going to use the same concept but for a different situation. So imagine the inner conductor. It's a cylinder, and of course when you put charge on the conductor, the extra charge, it goes to the surface. And what does it mean if I say that the charge per unit length here is plus 2 lambda? It means if I go a certain length L on the conductor and I calculate the total charge on the surface as you go down this length L, the total charge, and it turns out to be, for instance, Q, then Q over L is the charge per unit length. And in the problem, we're giving it to be equal a value of 2 lambda. So that's what we mean by charge per unit length. So the charge per unit length, simply, it's the total charge as you go down. It's the charge on a surface. It's not charge on a line, on a contour anymore. It's charge on a surface. As you go down, you calculate the total charge on the surface and you divide by the length that you went. That's what the charge per unit length is. And in the problem, they just said it's equal to 2 lambda. 2 lambda meaning that it's, the reason why they give it as 2 lambda is because they're giving the outer conducting shell to be of a charge per unit length minus lambda. So they're showing that the inner conductor has a more charge per unit length than the outer. That's the, I mean, we could have called Q over L lambda of the inner conductor. We could have called it that, but it just turns out in this particular problem that the charge per unit length on the inner conductor, on the solid conductor, is given a value 2 lambda, and that it's twice the charge per unit length on the outer spherical cylindrical shell with an opposite sign. So again, the charge per unit length on the solid inner conductor, this one, it's 2 lambda, and the charge per unit length on the outer cylindrical shell is minus lambda. So the 2 and the minus, this is just trying to show you the relative charge per unit length between them. That's why it's given this way. So this problem is exactly the same as the other problem that we did before with the 2 spherical conductors, where we had charge 2q on the inner one and minus q on the outer one. This is the exact kind of analogous problem in cylindrical geometry. So the same as we did before, we want to find the electric field from 0 to infinity as you go along the radial direction, and also we want to know how much is lambda inner and how much is lambda outer. We know that the charge, this charge minus lambda, it's distributed, part of it in the inner surface and part of it on the outer surface. So we want to know how much they are. So let's look at the problem from above, just again to get a nice picture. If you look at the problem from above, it appears in maybe a simpler way. This is the inner conductor with radius A. It has charge per unit length 2 lambda, and this is the outer conductor with a cylindrical conductor. It has charge per unit length minus lambda, and in between is empty space. And remember, these are cylindrical conductors. So let's try to solve the problem. What is the electric field between 0 and A? Since the region between 0 and A is inside the conductor, and the conductor is in equilibrium, then the electric field is 0. So it's a very simple result. Okay, what about between A and B? How would you get the electric field in this region? Well, we need to use Gauss's law, and to use Gauss's law we need to choose a Gaussian surface. So we're going to choose this dotted cylinder. And the cylinder has a height h, and it has a radius r. If you look at the top surface of the cylinder, the area vector points up and the electric field vector points radially outward. The angle is 90 degrees. And for the lower surface, the area vector points down because it points from inside to outside, and the electric field points radial and the angle is 90 degrees. So the flux for the top and lower surfaces when you use Gauss's law is 0. For the side surface, the electric field and area vector point in the same direction. So the dot product becomes E dot dA becomes EdA. Okay, so now let's use Gauss's law. So Gauss's law, the left-hand side of Gauss's law has 3 terms. You have the sides, you have the top, you have the bottom. And we said before that the flux through the top surface and the bottom surface is 0. So this is 0 and this is 0. The only one that survives is the flux through the sides. And for the flux through the sides, the angle between electric field and area vectors is 0 everywhere on this cylinder. So E dot dA becomes EdA. And then from symmetry, if you get the electric field here or here or here, anywhere on the cylindrical surface that has a radius r, the value of the electric field would be the same. We don't know what the value is, but we know it's going to be the same value from symmetry. So you can say that the electric field is constant and it goes out of the integration, so it becomes E integration of dA. So now what's the surface area of the sides? Well, the side surface area, it's the same as the area of a rectangle that has one side h and another side the circumference. So what is the total area then? The total area is 2 pi r, which is the circumference, times h. So the left-hand side of Gauss's law simply becomes E times 2 pi r h. Okay, what about Q inside? How much charge is inside this dotted cylindrical Gaussian surface? Well, the total charge inside is on this cylinder, and it's on the surface of the cylinder. And we know that we're given that the charge per unit length is 2 lambda. That means if you know what the charge per unit length is and you want the charge in a certain length, then the total charge in a certain length of h is the charge per unit length times the length. So it's 2 lambda times h. So the charge inside this dotted cylindrical shell, Gaussian shell, surface is 2 lambda times h. So now we know the left-hand side, we know the right-hand side, and you can see straight away that the h will cancel with the h, and the 2 will cancel with the 2. Well, let's not cancel the 2, we'll keep the 2. So then the electric field turns out to be 2 lambda over 2 pi epsilon naught r. So this is the final result for the region between A and B. Okay, what about the region between B and C? So in this region between B and C, the electric field is 0 because you're in a conductor in equilibrium. So the electric field is 0 between B and C. It's very easy. What about bigger than C, for a radius bigger than C? When a radius is bigger than C, you can make another Gaussian cylindrical surface, this dotted surface, and the same thing happens like before. The area vector and electric field vectors are 90 degrees with respect to each other for the top and bottom surfaces, so the flux is 0. The only contribution comes from the side surfaces where the electric field and area vectors are in the same direction. So you can say exactly the same as we did before, that the left-hand side of Gauss's law is E times 2 pi r h. But now what's the charge inside the Gaussian surface? Well, part of the charge inside the Gaussian surface is the charge on this inner conductor, and part of it is the charge on the outer. We know the charge per unit length on the inner conductor is 2 lambda, so that means the charge in a certain length h is 2 lambda times h. That's the charge of the inner conductor, and we know that the charge per unit length on the outer conductor is minus lambda, so that means the charge in a certain length h is minus lambda times h. So that's the charge on the outer conductor. So the total charge inside the surface is then 2 lambda h minus lambda h, which is just lambda h. So we can substitute this into Gauss's law, and the H will cancel with the H. We get the final result that the electric field is lambda over 2 pi epsilon naught r. Okay, now we want to know what the charge on the inner charge per unit length is on the inner surface and the outer surface. So we're going to do exactly the same thing we did for the spherical case. We're going to make a Gaussian cylinder, but the Gaussian cylinder, this part of it is inside the conductor. And what's the reason we choose this Gaussian cylinder? The electric field is zero inside the Gaussian, inside the conductor. And for the top surface and the bottom surface, the electric field and area vectors are 90 degrees. There's no flux through the top and bottom surfaces. And for the side surfaces, the side surface is completely inside the conductor. So the electric field is zero. So the left-hand side of Gauss's law is zero. That means that the charge inside this dotted cylinder has to be zero. So let's see how much charge there is inside this dotted cylinder. There's charge, obviously, 2 lambda times h for the inner conductor. And then there's charge what? There's charge lambda inner times h for the charge over here, for the inner charge. The outer charge is outside the cylindrical surface, so we don't put it. We only look at the charge inside. So the charge inside, you only take the lambda inner times h. So that means when you put this together, you get lambda inner is minus 2 lambda. Okay, and then we know that the total charge per unit length on on both surfaces is minus lambda. So that means if you go on a certain length L of this conducting shell, the total charge in the length L will be minus lambda times L, and some of that charge is on the inner surface and some is on the outer. So we know that lambda inner times L plus lambda outer times L has to be equal to minus lambda times L. That's what we know. That's given in the problem, but we don't know how much lambda inner is and how much lambda outer is. So if you cancel the L and you cancel the L and you cancel the L here, you get this equation. But we have just derived just now what lambda inner was. Lambda inner turned out to be minus 2 lambda. If you plug this into the equation and you put on the right hand side, you get plus 2 lambda minus lambda, then the lambda outer turns out to be plus lambda. So the final conclusion is that lambda inner, the charge per unit length on the inner surface here, is minus 2 lambda, and the charge per unit length on the outer surface is plus lambda. This is the summary of the whole problem. The charge per unit length on the inner and outer surfaces is as given. The electric field is 0, less than A, and between B and C. And then between A and B, the electric field is this value. Between bigger than C, the electric field is this value.